our project, named on a method for finding position and orientation of accelerometers from their signals. This is a joint work by Hongxinyi and Yang Qizhen. Here's a quick overview of today's presentation. We'll start with the abstract introduction and comparison, move into the mathematical modeling, accelerometer signals, and optimization method, then share our expected result, and finally conclude with the key takeaways. The core idea of this study is to estimate the position and orientation of accelerometers using only their own major signals. No external measurement tools like cameras or markers are needed. This makes the method especially useful for compact or low-budget setups. Some key points in this paper. No external measurement devices are needed. Uses rigid body motion and numerical optimization. Applicable to structural dynamic testing, and it is low cost and efficient for small-scale vibration analysis. Accelerometers are widely used in engineering for structural dynamics and vibration analysis. However, traditional steps requires manual measurement or optical systems, which can be expensive and inconvenient. Our proposed method is completely self-contained. It relies on rigid body motion assumptions and mathematical modeling to infer the accelerometer's spatial configuration. In this paper, also compared the method with self-calibration of accelerometers array, SCAA method, which can find accelerometer's position and orientation directly from the measured accelerations. The other method except these two are needed dedicated calibration machines, which is complex and expensive, don't need to be used in SCAA method. This is one of the SCAA method advantage. Some similarities between these two methods should be presumed as a rigid body movement and required at least 3 triaxial accelerometers. Differences. SCAA can measure from 0 Hz, cause IMU application. The other one is excellent at higher frequencies, but failed to measure very low frequencies due to miniature piezoelectric accelerometers used. SCAA can significantly change its angular orientation, and the presented method assumes small translational and rotational magnitudes. Their optimization routine is different. The most significant reason is SCAA method retains the centripetal term, while the proposed method drops it. Whether using the centripetal acceleration component or not will affect their applications. Both of these two methods have their own pros and cons. We should choose the appropriate one to use, depending on our problem situation.
Let's now look into how we model a problem mathematically. We assume the object carrying the accelerometers behaves as a rigid body, meaning the relative position between the accelerometers do not change during motion. The motion is described using tight Bragg angles, yaw, pitch, and roll. We decompose the total acceleration measured at each sensor into 3 components: translational acceleration, rotational acceleration, and correlates acceleration, and this is the equation. This expression gives us a theoretical model of what acceleration values should be measured, given a certain orientation and position. In 3D orientation and rotation representation, tight prime angles and Euro angles are both commonly used, but they have important difference. Tight prime angles, these are a set of 3 angles used to describe an object's rotation in 3-dimensional space. They are usually defined by a sequence of rotations around a specific axis, rho, x-axis, pitch, y-axis, and yaw, z-axis. The rotation order can vary, like z, x, y. For Euro angles, similar to tight prime angles, but the rotations follow a fixed sequence, such as z, x, z, yaw, pitch, yaw. They are used to describe an object's orientation by specifying 3 rotations around the axis of coordinate system. In conclusion, tight prime angles have flexible rotation orders, whereas Euro angles have a fixed rotation sequence. Tight prime angles focus on rotations around individual axes, while Euro angles involve multiple axes in a fixed order. Here's a visual representation of rigid body motion. Every accelerometer on a body experiences motion derived from the same rotational and translational source.
Accelerometers are widely used in our mobile phones. I have searched for an application called 5 which can receive acceleration and gyroscope data with respect to time. Therefore, we can get accelerometer signal by phone's inner accelerometers. This app also can transfer signal wave chart to Excel tubular data. The result I operate practically. Picture acceleration 1 of 1 and 1 of 2. I move my phone toward north. We can see x-axis x-axis has the highest value. Thus, we predict that this path directly related to x-axis. In picture 2 of 1 and 2 of 2, I move my phone toward arbitrary orientation. Therefore, each of the axes have varying Therefore, each of these axes have varying waveform. This data is from gyroscope. Picture gyroscope 1 of 1. I rotate my phone on desktop. We can see z-axis has obvious fluctuations. We can boldly speculate this rotation axis is your axis. Picture gyroscope 2 of 1 and 2 of 2. I rotate my phone perpendicular to the desktop. Also, we can speculate this may be pitch axis because y-axis has the most fluctuations. The other two both just near 0. We can see some small noise because I move cell phone with hands and the application is very sensitive. If the cell phone against the desktop, it may reduce some noise. mostly used in our reports. Maybe we can put several mobile phones on objects, such as a manned vehicle, weather balloon, car, etc. Therefore, we can receive accelerometer signal. But when I compare values from acceleration and gyroscope from Excel file, they have different time interval value. We can see in this column and that column. For example, acceleration starts from 0.0214, have 0.01 interval value. However, gyroscope starts from 0.0139 and have 0.0025 interval value. This problem may because different sensors may have different detection frequency. Such time value can match problem. Real complex are stem from real detected value to accelerometer signals. Therefore, I think Firefox isn't a really appropriate tool to be used. Another way to detecting is to programming and let our mobile phone connect with program. Then directly show acceleration and gyroscope at the same time. The reason why I didn't use another method is because this program may change my phone's original settings and may produce some unpredictable errors on my phone.
Next, let's talk about how we estimate the unknowns, position, and orientation. Step 1. Define the error function. We first define an error function that quantifies the difference between the actual measured accelerations and those predicted by our model. Step 2. Minimize the error. Then we use optimization techniques such as gradient descent or nonlinear least squares to minimize this error and recover the unknowns. This approach is particularly effective when the rigid body motion is sufficiently diverse and well excited. To give this a practical meaning, we simulate real-world noise by generating synthetic accelerometer signals with added Gaussian noise. Then we compare the predict signal against the actual measurement and calculate the root mean square, RMS, of the error. In our example, the RMS error turns out to be approximately 5.3% of the signals on our RMS. This provides a reasonable benchmark of how close our prediction is to reality. Here, we show a visual comparison between the reference signal and our predict signal. In the top plot, the blue line represents the measured acceleration from a reference accelerometer, while the red dashed line shows the predict signal. In the bottom plot, we plot the error signal essentially, the difference between the two, which allows us to visually inspect how well our model is performing over time. This kind of comparison helps us not only compute quantitative errors, but also diagnose patterns in the deviation, which might inform future improvements to our prediction model. This type of visualization is very similar to Figure 7 in the reference paper, where the RMS error is also used to evaluate feeding quality. In this measure, the difference between the measured and predict accelerometer signals. By varying parameters like amplitude and phase, we calculate the error for each combination. This results in a 3D error surface, where the x-axis represents amplitude values The y-axis is represent the face value, and the z-axis represent the RMS error. The goal is to minimize the error lowest point on the surface to find the optimal parameters that best match the measured data. This method is useful for sensor calibration and improving model accuracy through optimization. The optimization process aims to estimate the position XYZ and orientation data of the accelerometer by minimizing the error between the predict and measure accelerations. This is a numerical optimization problem where we adjust the model parameters to minimize the error, thus obtaining the best position and orientation estimates. After optimization, we obtain the best position and orientation parameters of the accelerometer, which minimize the error between the predict and measure accelerations, accurately reflecting the true position and orientation of the accelerometer. So the result of it is the position X, Y, Z, and this is the optimization data. Based on this method, we anticipate the following results: accurate estimation of accelerometer position and orientation, works even when only relative distance are known, applicable to small-scale vibration analysis, and more affordable and time-saving than traditional setups.
To conclude, this method removes the need for external tools. It uses only accelerometer data and mathematical modeling. It's suitable for many practical applications, like structural monitoring or embedded systems in robotics. Thank you for your attention.
Okay, good. Good job. A few comments, okay, before we leave. Number one, whenever it is possible, I would prefer you to include a picture, a photo. For example, in the page, for the introduction, and yeah, you mentioned about like structure dynamics, something like that, okay, vibration analysis, okay? Put a small picture right next to the points, 1, 2, 3, okay, number one. And also in the next page, you mentioned about some points here. I think it would be better if you can indicate what is the benefit, what is the advantage. Usually we call this pros and cons. Yeah. Indicate the advantage of using this method is, okay, we call this the pros and cons. Thank you. Okay, whatever, right? Okay, then what is the pros? Pros means advantages. Advantages. Okay, so we have some points. What is the advantage of using this method, right? Another one is the cons. What is the downside? Okay, or we call that not bad, but okay, so you can mention that using this method we have several good points, but at the cost of whatever. We have to spend some cost, right? In order to achieve those advantages. Okay? Okay, that will be very good. And then, hold on, sorry. In the next few figures attached, those figures. Yeah, okay. You are supposed to present your paper in English, right? Don't use Chinese character in the report. Because in case this will be a paper in a conference, international conference, then we will assume most of the readers or most of the audience in the room cannot read it. Okay? We only can read English in some sense. Okay? So convert those Chinese characters to English. And also, one of the most important things is here. You use the X direction, Y direction, and Z direction without defining them. You have to define your coordinate. What is the x-axis? What is the y-axis? What is the z-axis? Define your coordinate. You have to sketch your coordinate. Yeah, you have to indicate what is your coordinate. Okay, specify the direction of the coordinate. Z means what? In the opposite direction of the gravitational acceleration or another direction. You have to define the direction of the coordinate. Where is the x direction? Where is the y direction? Where is the z direction?